Hello, in this video you will be taught as to how to deal with the special right triangles and in the unit circles and where did those come from and conceptually how to understand the values in the unit circles. Before we begin, this is strictly based upon the knowledge of how one of the ways in which we can solve for sine, cosine, tangents of what we call special right triangles. So there will be two of them called 30, 60, 90. And there will be 45, 45, 90. And if you guys search that up on Google and look it up online, there are a whole bunch of formulas that you guys can look at. But the main question is, do you guys understand conceptually as to how those came to being, and are you able to explain it as if you're trying to explain it to a 5-year-old as to how this thing came to being? Okay, so first let's take a look at the unit circle values. Now, if you were to just take a look at this as a whole thing, there's a lot of information that you need to take in. What we need to first focus on is the first quadrant here. And as long as you can understand where these values came from, because that's mainly just meant to be for Algebra 2. If you guys know, the values of the unit circle is nothing more than using the special right triangles, because these are what we call the special triangle angles 30, 45, and 60. Those are what we're going to explore. But these values that came with it, the x and y coordinates, they're all mainly from the sine, cosine values of those angles. And before we begin diving into the unit circles, which is mainly meant for Algebra 2, we have to take a little bit of a step back towards geometry portion of where this unit circle came to being. Well, first of all, you guys all have to understand that a unit circle means simply that the radius is always going to be 1. So you have to keep that in mind when we're doing these problems here. And so let's go to the next slide. So special right triangles. The very first thing I'm going to take a look at here is an equilateral triangle. Okay. So what does equilateral triangle mean? Well, equilateral triangle is anything that has 3 same sides and also has 3 separate angles that are exactly the same. As we know, this is not even geometry. It's very, very simple. Just geometry 101 stuff. It's all the angles that adds up. That's interior angles in a triangle adds up to become 180 degrees. That should be said, without question. If we consider these 3 angles to be exactly the same, then we have to simply split the 180 into 3 equal portions, which will simply give us all 60 degrees. So that's the basics of special right triangles or the equilateral triangles. Now, from this, if we were to simply cut this in half like this triangle right here is called 30, 60, 90 triangle because we're essentially cutting this angle in half. The property in which we're going to cut this in half is because these two sides are the same. Any isosceles triangle that we have, not even equilateral and isosceles, if you were to draw a perpendicular line down from this vertex, you will get this angle and this angle to be the same thing. So if you take any equilateral triangle and also cut, fold it in half, do whatever you need to do, this angle and this angle should be exactly the same. Okay, so now what we're going to be considering is a triangle that looks simply like this, where the angle here would be 30, angle here would be 60, and angle here would be 90 degrees because obviously that's going to be perpendicular to this line and the base. Now, since we have this half of an equilateral triangle, before we jump the gun into the formulas, let's take a look at the values if we were to assign anything. So let's say, for example, hypothetically, I would like to call this side length of 2. Let's use blue. Let's call each of these length to be 2. Okay, just for the sake of understanding the equilateral triangle and the special right triangles. Now, if we were to cut that in half, the only side that really remains the same is this side right here, which is still 2, right? Because that's still the only one side that gets maintained and gets preserved from the previous equilateral triangle. Now, the missing portion, the other side of the triangle that we folded up, this side here and this side here has to be equally the same. But what we have essentially done is that we cut it in half. So this side is really easy to get. It's just simply going to be 1. It's just half of whatever the side of the equilateral triangle is going to be. You can literally do this with a piece of paper. You fold this in half. That's 2 and that's 1. That should be said no matter what. So what is this other side going to give me? Well, this is most likely not some things that you learned in a 5th grade. I hope you guys all remember Pythagorean theorem. It's one of those things that in geometry that you guys have to remember is that states that any right triangle can be solved given A, B, C. C squared equals A squared plus B squared. Okay, that should just come out. It's not something that's, I'm pulling it out of a, heavy textbook. It's got to be somewhere. It's got to be somewhere in your brain. Okay, that's got to be a memory space right there. So now that I have this formula with me, I can actually take that and solve this. Remember, the only thing that you have to remember is that the longest side, this, is your C value. So C squared equals A squared, doesn't matter which one you would call A, plus question mark squared. It gives you 4 is equal to 1 plus question mark squared. If you were to do the algebra, subtract the 1 on both sides like this. 3 equals question mark squared. So the question mark actually becomes a square root of a 3. Okay, so why am I telling you all this? It's because no matter what you do in any circumstances, these 3 ratios, okay, 2, 1, and square root of 3, will hold true. It will hold true no matter what type of triangle, no matter what type of 30, 60, 90 triangle you will ever have. So, for example, if I have a small 30, 60, 90, a medium 30, 60, 90, or even a very large 30, 60, 90. Okay, that doesn't really look like a 30, 60, 90, but bear with me here. Okay, all of these triangles are called similar triangles. Okay, and because they're all similar, even though the side length may be different, but the ratio will be preserved. So if this side is root 3, 1, and 2, and if you were to double each of these sides and say 4, 2, and 2 square root of 3, those ratio will hold true for every single triangles that we'll see. Okay, so on the next slide, this is usually the textbook definition in which what you will see. So if we have any special right triangle on the right hand side, and if we call this length right here as S, that's opposite from 30, we call that side the side that's facing the angle. That's S. Well, we know then AC is S root 3, and AB is just simply double the S. Just like the one that we have done before, 1, root 3, and 2, we can take that and say, okay, whatever the smallest side is, whatever the side that is opposite from 30 degree was, we have to simply multiply that by root 3 to get the 60 degree side. If I were to color code it, that would be the 60 degree side. And the 90 degree side will be simply doubled whatever the smallest side was. That ratio will hold true no matter what. If it was S, if it was 1, or if it was a blob, or if it was a 2, no matter what it was, no matter what it is, that will hold true. To give you a couple of examples here, let's take a look at these two. I know the picture came a little bit awkward, but let's take a look at these two. Now, I provided this chart for you here to do the trigonometric ratios behind this, but let's say first I'm asked to solve for these two triangles. Let's say I'm asked to solve for, okay, what's PR and then what's PQ? Because those are the missing lengths here and here, right? Well, the only side that's given to me is opposite from 30, which is a 6. Okay, so I'm given 6. What we also know is that this side, PR, is your longest side because that's opposite from 90. And what is the relationship between the smallest side, 6, to your longest side that's opposite from 90? Well, if we go back, we find out that whatever was given to me as S, you just simply have to double it, right? So if that was 6, what would this be? It would simply be 12. That's it. You just simply have to double it. And what would this be right here? Well, if I'm given the smallest side, just from the previous slide that I gave you, this side, you would just simply have to multiply by root 3. So I will take the smallest side and then multiply by root 3. This also gets a lot of kids to be confused. Do not write square root of 18 because they think, oh, 6 times square root of 3 is square root of 18. That's a really common mistake that we all encounter. You just simply have to multiply the integer value separate from the radical. You just have to put it next to each other. So it won't be square root of 18. Just scratch that out of the way and just put 6 square root of 3. That's how you would write that. It's like 6 times x. You write 6x, just right next to each other. Okay? So you have these two values here. Now, let's take a look at the other triangle, which is given to me as 9 square root of a 3. Now, how would you be able to solve for that one? Now, I'm given the one that's opposite from 60 degrees. Okay? Now, to find the one that's from the opposite from 30, let's say I call this side length as S. From the previous slide, what we know is that this side right here, the 60 degree side, the formula for the 60 degree side was S root 3. So if we were to call this as S root 3, notice how I can just simply set those two things equal to each other and then solve for S by simply dividing the square root of 3's away, and gets me a really nice number for my side length S. That's right, it just simply becomes a 9. And if you guys were to do the same exact problem as how we solved for this question, smallest side to the 60 degree side was times root 3, just like this one right here. So it checks out. And once I have the smallest side, it's really simple for you to find the longest side. I just have to double it and gives me 18. Okay? And also, if you were like to think of it this way, if I were to take all of this out of the way here. Ooh. If I were to take just all of this, delete. Imagine for a second what would happen if I were to complete this other half of this triangle. See, if this height was 9 root 3, if we find out that was 9 and we found that was 18, that means that this entire triangle that we have would be equilateral triangle, and that was the very first thing that I've taught you, right? That we split the equilateral triangle into half of it, and that would just give me the 30, 60, 90 degree triangle. Well, if that's the case, and if I double this side, that's 9 plus 9. Does that give me 18? Sure it does. So that's 18 here, that's 18 here, and that's 18 here. So it goes back to the equilateral triangle. So visually speaking, that's also another way that you can envision it. But that's actually beside the point. We don't really have to go through that much extent. Okay, so now let's take a look at the trig values, because this is what's really important. For both of these two triangles, what we have is sine, cosine, tangent of these two angles specifically. Now, trying to find out the 90 degrees is a separate question, but we simply cannot do opposite over hypotenuse on a 90 degrees, right? So, but if you guys type that into your calculator, what we can do is we can assume it by using what we call limits, but that's beside the point. We don't really have to work on that far end. Okay? Now, sine of 30 degrees, what would that be? Well, sine, as we know, if you guys don't remember SOHCAHTOA from your geometry class, we need to first figure out how to do this by first finding all the missing lengths. That's your number one step. Once we have that, because we're only talking about sine, cosine, and tangent of these two angles, go to the respective angles. So I'm going to go to the 30 degrees. And what we have is always we have the three sides called opposite, adjacent, and hypotenuse. Okay, so let me just erase all this. Okay, and so I'm going to relabel this as this is 6 root 3 and this is 12. Much cleaner this way. Let's first talk about 30. What's opposite from 30 degrees? Well, it's the side that's facing the angle, right? So this is your opposite. This is your adjacent because it's right next to it. It's the side that is adjacent to the angle. Or if you want to remember it as the hypotenuse is the longest side, it's simply the other one. So we have the O, A, and H from all of these three sides. So what is sine of 30 degrees going to be? Well, it's simply opposite over hypotenuse. It's 6 over 12. Now, can we reduce that? Yes, you can. It's going to be 1/2. Now, before we go to the cosine of 30 degrees, let's take a look at this other triangle that we have on the second problem. I'm going to erase all this stuff as well. Sine of 30 degrees, what would that be? Well, sine of 30 is your opposite side from here, adjacent side from here, and your hypotenuse, which is your longest, that's opposite from 90, will always be your hypotenuse. The way I remember it is, the one that mostly is going to be a diagonal turns out to be a hypotenuse at the end. Okay, so now I have 30 degrees, opposite, hypotenuse. What will that give me? 9 over 18. Simply the ratio of opposite over hypotenuse, right? Reduce that, what will I get? 1/2. Take a look at what I end up with. Even though these two are number one, number two, two separate problems, two different contexts, different numbers, different how to solve the question because they're giving me two different things. At the end of the day, what happens to the trig ratios? They all end up being 1/2. And the reason why that is because just like I mentioned to you before, these similar triangles, doesn't matter how small or how big it gets, your trig ratio will always end up being 1/2. That's why when you go to your calculator, TI-84, whatever, if you type in sine of 30 in degrees mode, you will end up with 0.5 because this will universally be held true no matter what. What type of triangle, how big, how small it is, it will always be 1/2. Okay, so now what about cosine, sine of 60 then? Well, sine of 60 here would be from this angle, right? Opposite would be 6 root 3 from that side. Hypotenuse would be 12. Now, just from before, we know that 6 over 12 will be just giving me 1/2, but the root 3 is right next to it. So the way to write it is root 3 over 2. From this triangle, the second one, the opposite from 60 is 9 root 3 over the hypotenuse of 18. So same thing happens when this 9 and 18 gets reduced. It gets root 3 over 2. Okay? So now I have found my sine of 30 degrees and my sine of 60 degrees. Let's take a look at cosine of 30 degrees. Well, cosine of 30 degrees is it's adjacent over hypotenuse, right? If we take a look at the acronyms, it's adjacent over hypotenuse, so we say SOHCAHTOA, right? So adjacent over hypotenuse from 30 degrees. 30 degrees is right there. And this is your adjacent side. So 6 root 3 over the hypotenuse of 12. Wait a minute, didn't we just do this before? Absolutely, we did it up here. So what it turns out is that as long as the angles are what we call complementary angles, I hope that this is all coming into the picture, that they add to give you something that's 90 degrees, sine of one of the angle is equal to the cosine of its complementary angles because, as it turns out, cosine of 30 is the same to sine of its complementary, which is 60 degrees. So we already have the answer for that. It's square root of 3 over 2. Now, do we have to bother doing the other triangle? I don't think it's necessary at this point that you can figure it out that similar triangles will still give you cosine of 30 even for the second triangle to be root 3 over 2. So using that figure, can we guess what cosine of 60 would be? It should actually turn out to be 1/2 because we know that sine of 30 is the same to cosine of 60 because they're going to be the complementary angles 30 and 60. 30 and 60, okay, 30 and 60 right there. And the trigonometric values, the sine and cosine values of those two things will turn out to be exactly the same. And now the final part is tangent, and tangent is SOHCAHTOA, opposite over adjacent. You guys can figure that out, and that's going to be no problem. The reason why I'm skipping this part is because for tangent, it's really not necessary for us to understand the unit circle part. Now for the 45, 45, 90 triangle, what we can do is simply we can cut the square into half, and if we were to call this either ones or twos, it doesn't matter what length it is, but if you were to cut this in half, you get one here, and then this diagonal one we don't know, right? Again, what do we use? Geometry 101. If it's one thing that high school geometry teaches you, it's trig and Pythagorean theorem. So you use that Pythagorean theorem, a squared plus b squared equals c squared, and then you plug that in and get this value. And you guys can always figure out how this formula came to being, which is on this next slide, s, and then s root 2. The beauty of this 45, 45, 90 is that two of them are going to be exactly the same. So it kind of cuts down the work for you by a lot. So S root 2. The reason why that is if I were to give you 1 and 1 here, 1 squared plus 1 squared equals c squared because the hypotenuse is the question mark, or maybe I should just use the question mark for this one. So if you were to do the math, 1 plus 1 equals question mark square, 2 equals question mark square, so question mark is square root of 2. So if you plug that in, that means that my hypotenuse ends up being a square root of 2. Then notice that the ratio here, if that was s, which was 1, then that other side should be s equal to 1 because these two are those two sides of a square. So if it's a square, that means all these four sides should be the same, right? Then the diagonal turned out to be square root of 2, but if the s was 1, if you plug it in right here, that's 1 times square root of 2, which simply becomes square root of 2. Now, what if I was given 2 and 2? What if I was given, I don't know, 3 and 3? Then it's simple. It's 2 square root of 2, 3 square root of 2. Whatever the s is, just put it next to the square root of 2. It's as simple as that. That's it. Just multiply by square root of 2. Now, if you were to do some of these problems here that you're given, now, just like before, pause the video now and try to see if you can do this on your own. Okay, now that you have the answers, this side and this side, they should be exactly the same because if you were to complete that square, all of these four sides should be the same. So if that's 7, that's 7. Another way that you guys can take a look at it is that if that's 45 and that's 45, and we call that the base angles, or isosceles base angle theorem, states that if the base angles are the same, then the sides are the same. The side that is opposite from these two angles. So if that's 7 and 7, what would this side be? 7 root 2. Simple as that. Now I'm given the hypotenuse as 12 root 2. So if I'm going in the opposite direction, what should I do? I need to just take away this square root of 2, right? So I should have 12 and 12. Very, very simple stuff. Now the next part is, how do I get the sine of 45, cosine of 45, and tangent of 45? For the sake of doing the unit circle, we're going to skip the 45 degrees for now. Now for sine of 45 degrees, it's always opposite over hypotenuse. For the first triangle that we see, let's take a look at where the 45 degrees angles here. That's the 45 degrees. You can use either one. But what is going to be the opposite? Well, that's your opposite, which is 7. And what about the hypotenuse? Well, that turns out to be 7 root 2. And when you guys do this, the 7s will cancel out and you will have 1 over square root of 2. Now, for the sake of doing the unit circle, what we do after that is something called rationalization. Maybe need to do one lesson on just straight up doing this. But rationalization simply means to get rid of square root of 2 or any square roots in the denominator. That's it. So how do we do that? Just simply multiply by the denominator to the numerator and the denominator. So what do I mean by that? The denominator says square root of 2, right? Multiply by square root of 2 over square root of 2. If that says square root of 3, multiply by square root of 3. If it says square root of 4, you get the idea. So that ends up being 1 times square root of 2 is just square root of 2. And square root of 2 times square root of 2 is square root of 4, but that's 2. So the whole reason why we need to do this, why in the world would we need to do this, bother ourselves by doing this, is because we want to make sure that the denominator is clean. We want to make sure that it's not something that's not pretty, like irrational numbers and so forth. So we want to make this to be clean integers. So that's why I know that it might really not make any sense and it doesn't really have any true purpose behind it. However, this is the way that they want it here. Now going back from what we talked about, sine of angle A is equal to cosine of angle B as long as those two angles were complementary. We talked about that from our 30, 60, 90 degree triangles, right? If these two statements held true, then what can you tell me about sine and cosine of 45 degrees? If both of these 45s are actually complements to each other. So if sine of 45 ended up being root 2 over 2, then believe it or not, cosine of 45 will give you the exact same thing, because 45 plus 45 is 90, and that means it's a complementary angle. So sine and cosine will give you the same thing. So to sum up, all of these values that you guys should have, that's square root of 3 over 2, and that's square root of 3 over 2. So all of these values that you have, what it turns out is that these values turn out to be the exact same values here. Take a look at the 30 degrees. and it's a unit circle, so I told you before that the length is going to be 1. But if you were to draw a line straight down and then go like this, what you will basically end up having is a right triangle with 30 degrees that looks like this, in which we have been dealing with so far. Now remember, every point in what we call this x and y coordinates turns out to be your coordinate in your Cartesian rectangular coordinate x comma y. This is your x, and this is your y. And remember, your hypotenuse or your radius of the circle will always turn out to be a 1. How do we get x and how do we get y? By using the angle and this hypotenuse. Well, it turns out it's quite simple. What is sine of 30? Well, sine of 30 is your opposite over hypotenuse, right? What about cosine of 30? This is opposite, this is adjacent, this is your hypotenuse. What about cosine of 30? Well, it turns out that cosine is x over 1 because it's your adjacent over hypotenuse. So what does that mean? It means that this Cartesian rectangular coordinates that you have, x is represented as cosine of 30, y is represented as sine of 30. In other words, for every single of these triangles that you can draw, this x coordinate, all that you see right there, is actually your cosine value of those respective angles. Cosine, cosine. And if you don't believe me, take a look at the previous slide. Take cosine of 30 degrees. Cosine of 30 degrees was root 3 over 2. And what do you know? It's root 3 over 2. Cosine of 45 was root 2 over 2. What do you know? It's root 2 over 2 right here. Last but not least, cosine of 60 is 1/2. You guys get the point, right? That's 1/2. Your x-coordinate for all of these unit circles will always turn out to be cosine of whatever the angle is, called Greek symbol called theta. That's the Greek symbol for angles. Don't ask me why. Then the y values, actually, if you take a look, those three values respectively, 1/2, root 2 over 2, root 3 over 2. I'll use a different color. 1/2, root 2 over 2, and root 3 over 2. They all turn out to be sine of that respective angle. So all of these coordinates that your teacher may be making you to memorize, it's not something that you end up memorizing. It's actually basically straight up facts from incorporating everything we know about SOHCAHTOA, sine, cosine, tangent, and how to deal with what we call special right triangles. Special right triangles. They all come together to make this hold true. So even though this chart makes not much sense if you just were to take a look at this as a glance, if we're to zoom in and break it down one by one, just little by little, it makes sense by using trigonometry, by using special right triangles, and etc. Now, eventually, when you get to algebra, the later pre-algebra 2 and pre-calculus, when we're asked to do trigonometric graphing and things like that, these values are so important, as well as these angles. These angles that you see here in degrees. These values are actually the most important when you're doing graphing, because they are actually the ones that's going to tell you your amplitude and those kind of things, but that's beside the point. For now, understand, just conceptually try to understand where these values came from, how to deal with 30, 60, 90, 45, 45, 90 special right triangles, and how to make sense of it by using something that you already know. An equilateral triangle cut in half, a square cut in half. Okay? All right, thanks for your time, and hopefully this video helped, and good luck in all of your other endeavors. Have a good day.